Hi everyone, welcome back to Feed Technologies. So with me again, Dito. So in this tutorial today, I'm gonna explain about pressure dependent modeling of polymers. So in the previous videos, I made more focus on modeling composite materials. I explained how to model cohesive elements, damage in composite, how to model composite with various scale, micro scale, meso scale. So in the next several videos, I'm going to focus more on how to model plastic deformation in various materials, including isotropic solids, sheet metal forming, which is anisotropic, and polymers. All right. Usually, people modeled anisotropic plasticity in metals using the von Mises criteria, von Mises plasticity, because they're very good. But for sheet metal forming, where the sheet has been through a rolling process, there is slight anisotropy in the rolling directions compared to the transverse directions. So the plastic yield strength is different. So in that case, you need to use anisotropic plasticity. For example, in ABAQUS, we have what we call, let me check here, Hill yield function. I'm not sure here, but should be there. Yes. For example, this one, ABAQUS has an isotropic yield function following Hill potential. And then there's so many types of plastic modeling, especially, for example, if you want to use the rate dependent modeling for plasticity, you have Johnson-Cook. Then you have several failure models that depends on, for example, plastic strain. We call it ductile damage. And there's so many other types of plasticity model, especially for polymers, rocks, right? Like Drucker-Prager, modified Drucker-Prager, Morcom plasticity. And we're going to see the tutorial about how to use that kind of modeling in the next video. So let's continue for today. I'm going to focus on Drucker-Prager models that is usually used for polymers. All right. So let's start by opening your ABAQUS, and then you go to this part module. So for this simplicity today, I'm going to try to model it using a cylindrical solid element. So you click here, create part. This video is supposed to be moderate level video. So if you don't know how to make part, go check my other videos, all right? Because I will not explain in detail here the 3D, the formable solids, because we want to make cylindrical solids. And then you choose this create circle, click here, and then you click here, right? And then put some dimension. Usually the dimension is somewhere between, 20 millimeters in diameter. So we choose 10 here, click enter. This is usually the typical, for example, if you do, so this is the typical dimension for specimen of SHPB. SHPB split Hopkinson pressure bar test. Okay, so this is high speed testing for material deformations. So the specimen is usually cylindrical solids, and then you perform impact tests on this. So the dimension is usually 20 millimeter in diameter. You close, you click down, and the length is somewhere between, 1 centimeters or even 0.7, right? So slenderness around 1. So I'm choosing 10 here. Yeah. All right. Or maybe let's choose 20 to make it more slender. All right. So this is how you modify it. You go here, section sketch. Section sketch, if you want to change the sketch, imagine you want to change the geometry. Instead of circular cross section, you want to make it rectangle cross section. So you can click here. But now you don't want to change that. What we want to change now is the extrude length. So you click here, so edit, and change it to 20, and click OK. It's longer. Sometimes if your geometry is very complex, it will not update by itself. So you need to right click here. There should be regenerate here. But in our case, we already automatically regenerate the geometry. So the next section is the properties. We want to assign the properties for this. This is the most important part of this video because we want to model this using Drucker-Prager plasticity model. So what you need to do is click here, create materials. So our materials here now is that having, for example, for PP, it's around 1.7 GPa. And then the Poisson ratio is 0.4. And I will give you another properties later. So this is 1.7 or maybe we should write 1700 because I'm using millimeters, so I want the unit to be MPa, millimeter, so it will be Newton per millimeter square, so it should be MPa. The Poisson ratio will be 0.4. This is classical elastic modeling, right? So if you want to model the pressure dependent plasticity model following Drucker-Prager, you can click here mechanical, and then you go plasticity, and then you choose. There's so many plasticity model, so different model is meant to be used for another type of materials. For example, this is for clay, this is for concrete damage plasticity, but in the recent papers from IMDA materials in Spain, they use it for modeling epoxy, for example. And then there's concrete smear cracking model. This is for concrete, this is for foam, and this is for rocks, right? There's many types. You can even use it for the materials that is not intended originally to be made. For example, like this concrete damage, it was originally developed for concrete, but now people feel that it is also suitable for epoxy materials. You can use it, right? So in our case, we are going to use Drucker-Prager. There's angle friction, flow stress ratio, dilation angle, right? So what the hell is that? So let me back to this ABAQUS manual. So the ABAQUS manual is enough for beginner, right? So if you want just to know the basic, you can read ABAQUS manuals. But if you want to know more detail, because for example, if you are a researcher or you're grad students, you need to read from books, from literature for more in-depth explanation and derivation, right? So let's come back to Drucker-Prager. Yeah. So this is the model that we use. It is called linear Drucker-Prager model. So there are so many types of Drucker-Prager model. At least in ABAQUS, there are three types. There is a linear one, there is a hyperbolic one, there is exponential one, right? In the linear one, it assumes that the yield function or yield stress will change linearly with respect to pressure. So this T is yield stresses, and the P is the pressure that you give in the specimen or in your elements. So P here is defined by the trace of sigma minus 1 divided by the P here is defined by minus 1/3 times trace of sigma, where trace of sigma means sigma 11 plus sigma 22 plus sigma 33. All right, so we are going to use this one. So this slope, the degree is beta. So the larger is beta, the higher is the pressure dependency. So the right side here, when P is positive, it means compression strength or compression case. When you are on the left side, P is negative, means that you are on tensile case. So this is usually has a lower tensile strength. In compression, you have higher tensile strength. So the difference between the tensile and compression is dependent on the parameters beta, all right? So this is what we call angle of friction. So for typical material, usually it's somewhere between 10 to 30 or sometimes 35 degree. So you can check that. So here, let's try maybe 20 degree. Yeah, you put in degree, and usually this dilation angle is also the same, 20. Not usually the same. This is a deep explanation. So this one, the angle of friction, just listen to me. And if someone asks you this is the answer, okay? The angle of friction is related to the yield strength difference. The dilation angle is related to the volume change, all right? If your dilation angle is big, like for example 30, 40, 50, it means when there is a plastic deformation, the volume change a lot. In classical metals, for example in von Mises plasticity, the dilation angle is 0. So when there is a plasticity, there is no volume change. There is no volume change during the plasticity. That is the classical von Mises model, where the dilation angle is 0. In this case, we have dilation angle is 20. So when the plasticity happens, there is a volume changes, right? So This value not necessarily to be the same like this one. If you put this 10, it also works. In this case, it is called non-associative flow rule. Non-associative flow rule. So if you read in papers when you're reading a manuscript in plastic modeling, they mention about something about non-associative modeling, non-associative flow rule. It means that the function that is used in yield strength definition is different than the function used in the plastic direction or delayed volume, not volume change, plastic direction calculation. So it's different function. That's why it's called non-associated flow rule. When they use the same function, for example, or the same angle here, they are associated flow rule. So in this case, we are going to see the case of associated flow rule. So I'm not sure I have to explain clearly. So there are two types of flow rule. Yeah, flow rule means this is how ABAQUS calculate the plastic strain direction. There is what we call yield function. This one determines the yield stress. All right. So there's a function F to calculate this. There's a flow rule. This is to calculate flow direction. So this is two different things. This is the yield stress. How big is the yield stresses? And this one is in which direction the plasticity strains, right? So this is calculating the flow itself, the flow direction. So in this case, the function is G. If G equals F, they call it associative flow rule. Means that when they calculate the flow direction, they don't use different function. They use the same function as F. When they're using different function, not equals to F, this is what they call non-associative flow rule. So it's as simple as that, right? Because usually people are afraid in the beginning when they read it for the first time. What the hell is it? Non-associative flow rule, associative flow rule. They don't understand. It's just simple as that. If you choose a flow function that is different from the yield function, that's called non-associative. If you use the same function, it's associative, right? So in Drucker-Prager, the F has angle of friction, right? And they are in our example is 20. So this one, guys, is related to volume change. All right, it's related to volume change. So if the G has also angle of 20, it means it has a lot of volume change during plastic deformation. All right, if the G has no degree of, for example, 0, no volume change during plastic deformation. All right, so in classical furnaces, F has 0 angle of friction and G has 0 friction. This is the classical furnaces. So there is no yield stress different in tensile and compression, no difference, because F has no angle of friction, 0 angle of friction, and also there is no volume change during plastic deformation, because the, how do they call this? The dilation angle is 0 too. But in our case, we're going to use both of them 20. That's why they're classified as non-associative flow rule. It has a lot of volume changes during the plastic deformation, and also it has a yield strength difference that we found in polymers usually. So when you do testing in polymers, when you do compression and tension, Usually the tension yield strength is lower, much lower than compression. In compression, for example, for PP you can go up to 40 MPa, while in tension you can go like only 1.17 MPa. So it's half lower than the compression. I hope my explanation is clear enough. If you think that my explanation is not clear enough, please comment below, guys, and tell me which part is not clear. I already repeat it here. I hope it's clear enough. Let's continue again. So what is flow stress ratio? What is flow stress ratio? So basically it's not in the original modeling of Drucker-Prager, but somehow during the time there's people proposing things to make it better for their materials. So the modification that they propose is this is in the T and P plane. So when you observe from this principal stress direction, the cross section usually is circular, right? But for some materials, they are not circular. They are like, I don't know, they call it three-lobe, or I don't know how they call this. So basically, the parameters to shift from this A to this B case is the K. If K is 1, it's perfectly circular. When the K is smaller than 1, they tend to be like a triangle, right? With a smoothed apex. So in our case, for simplicity, we don't want to deal too complicated things. Just assume one. Why? Just choose circular cross section, especially because during the test we cannot do so many tests to test everything, right? We have limited materials and we are too lazy to do the test, and our boss wants us to make paper in a very fast pace. Of course we cannot make like 100,000 tests just to get every single parameters that we need. So we need assumption when we do the simulation. So for example, in this case, because we don't know, we choose one. So we assume that they are circular cross section. And there's shear criteria, there's linear, hyperbolic, exponent, as I showed you before. In this case, we are going to see the linear one because this is the simplest one. And then you click OK. And then the rest is the same. You can click continue, and then you can assign it, and then you click OK, and then you go to the assembly, you assemble them, and then you can click OK. I will just skip it very fast, right? Because I don't want to spend your time too much. And then incrementation, this is just easy because this is plasticity, no damage, so you don't need to take care of the stabilization of everything, just like this. And then I want to create output that has space-time intervals every 100. All right, what else? That's it. Oops, where was it? I misclick. Okay, here the history. Imagine I want to check the plastic dissipation. I want evenly spaced time intervals, and the energy, I put all the energy, right? They will have everything, plastic dissipation and all that stuff. It's complete. And now I will go to interaction. Oh, there's no interaction here because we are going to fix it and pull in one side. So this placement here, I'll click continue. This side I will just simply click done. Oh no, yeah, click done. Just fix it. No point to constrain this rotation because this is 3D elements. So remember this again. In 3D element, there's no translational degree of freedom. Okay. And then you can rotate this guy, and then you can how you call it? Yeah, you can push it downward. This and the minus Z is minus, I don't know how, minus, this was 20. If I want to give, for example, 5%, you want to give 5%. If 10% means 2, 5% means 1. Okay, I compress, yeah, I tensile them, minus 1. Okay, Oh, and I forgot, guys. I forgot. Let's come back to the properties. You edit. This is only about the plasticity, but you need also to provide them the hardening curves. So the hardening curves is here, Drucker-Prager hardening. So you need to tell the ABAQUS that this is the example. I will just make up easy for a fake data, huh? Just to give you example. This is not really fake, but because the value will be related to epsilon p. When the plastic strain is 0, it means that during the beginning of the yielding, the yield strength is 20 MPa. During 1%, they are 25. And then during 5%, they are 30. Okay, so this is the hardening curve. If you draw this, I'm not sure, I don't know how to draw this in Google Sheet. Maybe here. Where is the diagrams? Yeah, so this is the curve. So there's hardening here, the yielding is at 20 and then it's hardened. All right, so let's put that down. 0, 0.01, 0.05, 20, 25, 30. 0, this one 20, 0.01, this is 25, 0.05, and this is 30. So if you have experimental data, put all the experimental data. All right, you need to put all the experimental data. In this case, this is just fake data, but this is quite related to the actual data that from the experiment, because I did the test for PP before. And the hardening behavior, you can have compression, tension, and shear. You also need to tell the ABAQUS what data is this, because this is pressure dependent properties. So when I tell, so as I said before, this is pressure dependent. So if you put yield strength, you need to tell them from which test, from what test you get this data. So in this case, let's say this is the tension data, because I understand that this is value that is related to the tensile test. And then click OK. And then you go to the mesh. This is simple. You click apply. Maybe just use one, so it will be small enough. Then click OK. Yeah, then click yes. And yep, it looks good. So, and now let's run the simulation. Create job. So this is tensile. We are going to do it 2 times. Okay, first we do the tensile, and then we do the compression, and then I will show you that the response are different because of this pressure dependency. I want to use 4 core because I have 4. Sorry guys. Oh, it's aborted. Why? The yield stress must not be 0. Oh, I made a mistake. So you go back. So this is important, guys, huh? When we draw a curve, the left side usually the x-axis and then the y-axis. So it's the plastic strain, right? The one on the x-axis, and the yield strain here. This is the typical way if we make our data in Excel or in Google Sheets, right? But in ABAQUS, it's a bit strange. I don't know what the hell's wrong with them. So it's the yield stress and the plastic strain. So you need to reverse it. You copy this to, oh no, it's better to copy this here to here. And then it's 20, it's 30. No, it's 20, 25, and then it's 30, right? Click OK, and then run again. So this is really important, guys. when you have something aborted, you check it, because I found many of my students come to me and then ask me, Dito, what's the problem? And then the error is very clear, but they just don't see it. See here, the yield stress must not be 0. So then I realized, oh, there's something wrong with the yield stress. Okay, I get it. I misplaced the location of the yield stress. Then you click submit again. We check, it's still running, right? It's running perfectly. Already 20% to finish. Yeah, guys, finally it finished, right? You see here it's completed. If you check this log, it says completed, right? Click dismiss and then click result. You see here, I hope it's good enough. You check here. Yeah, so it's really nice, because here we fix, so there's like, I don't know how, like not a knacking, but a smaller cross section in the middle for us make sense. So now, how to post process it? For example, I want to get the reaction force. Okay, so now how to post process it? For example, if I want to get the reaction force, you can just simply do it like this. Yeah, put in this YZ plane and then choose this, turn off the perspective so it's easy to choose. I'm not sure which part is being pulled and which part is the one that is resisting the pulling. So just play. Oh, so it's pulling on the left side, so we can get the reaction force here. So you click here, create XY data, ODB fill output, you click continue. You want to get the reaction force. Hopefully I click it. Make sure it's unique nodal, because you want to get the data from each nodal. And then the reaction force here is the reaction force in the Z direction, so it should be RF3. And then you click edit, and then you choose all these, making sure you only choose here. Okay, so how to do it? Return again to YZ. It's here, right? So you click edit, and then you click here and drag, and then release your mouse. Okay, and then you click done. Should be, there's 483 in my case. You click save, and then you click OK. So it will save. How to check? You click here, XY data manager. There's so 483 data for each nodals. All right, but now what we want is to know the reaction force, the total reaction force. So what you need to do is to process again this data. You can create ODB fill output. You don't click here. You want to operate on XY data here. You click continue. So this is the existing data. You want to sum all of them. So you click here. There's option here what kind of operation you want to apply. There is sum. Oops, click 2 times. Let's delete. Sum of from here, click here, and then you go here, you pull, and then you click shift, and then you click here. So, and then add to expression, and then you save as, you call it sum of F, sum of, and then you close this, and this is the data. So you can plot it. You see, this is the data that we just get. So let's copy paste this to Google Sheet. I'm not sure Google Sheet know how to handle this because because I'm not sure how to change these, because there's a problem with my Google Sheet. It used the comma instead of the point. for decimals. 0.1, 0.1. If you multiply this times this, it shows error because it didn't recognize the commas, the decimals. It didn't recognize the point as decimals. You need to do it like that. Yeah. So I don't want to change it again. Let's check. Okay, Indonesia. Oh. Okay, Indonesia. Like function. I don't know. Let's change it to US. Yeah, because in Indonesia we use comma as decimals. Where's the US? There's no US. Oh, here, right? Where was it? Yeah. So now it's great. So for example, let's move. Wait. Some of them still has this. For example, let's recopy paste it again. You can double click it and it will appear. And then you go here, click here, and then go and paste. All right. Let's check. Copy this, multiply by this. So the format is correct, right? So this is this time, and this is stress in MPa during the tensile. All right. Now we want to check during the compression. So let's redo the simulation, but first let's reverse the loading. Instead of pulling, let's do it positive, so it will compress. All right. You click job and then you do create compression. You continue. Let's use 8 core to make it faster. Alright guys, so now it's already finished. Let's check it. Result for the compression. So when you redo the simulation with a new simulation, with a new job, the previous data that you extract will still be there. So you don't want to confuse. So you don't want to confuse it with the previous data processing. So it is better to remove it. You click delete and yes. And then make sure this is the compression. You create, you choose the source from the ODB, you click continue. And then this is the reaction force. You click here, put in the YZ plane again, choose here. So there's a barreling here. So this phenomena called barreling. So the diameter is getting bigger, especially in the center of the cylinder. This is very typical because here you fix the surface of the specimen. So during the split Hopkinson bar, this is the extreme cases where we don't give the permission for the specimen to have this lateral expansion, right? So this is called confinement effect. So in real situation, it is not dominant like this. Why? Because the only thing that prevent lateral construction is the friction from the interface of the bar, the pressure bar, and the specimen. And usually it's somewhere between 0.05 to 0.2 if you have a very nice lubrications. So the barreling that you see in the real experiment should not be as big as this one. You click edit and then you select again. Where was it? Should be here, right? The reaction force is there. And then you click don't. And then you click save. Click OK. And this is the data you can create, and then you can operate on this data, and then you click, or you can type sum. I prefer to type, You return to the middle of the bracket of the, and then you add to expression, you save as sum of x, sum of f for com, and then you click OK. You get the data here, the less data, and then you click here, double click, you get the data here, and then you click here, you copy, and then you return again to your spreadsheet, you copy paste, but make sure first you take the absolute value of this guy, because now we just want to compare the absolute value, not including the, not including the direction. So we just want to have this guy. And so to make it easy, I will just move this guy to here, and I will just move these two columns to here, and I will just try to plot them together by the diagrams. Yeah, this is the first one in tensile, and then let's copy this to here. Hopefully it works. When we compare, there is a different compression, and then you go down, you do it again, diagram again, and let's superimpose them so you can clearly see the different. Why it takes so long? It doesn't really good, huh? Google Sheet is not like as powerful as, I cannot even move it. Okay, I click copy and then I paste. Oh, I cannot do it, guys. How to, imagine I change it, edit diagrams. Imagine I want to edit diagrams, and then I want to add more series. How? I don't know. I don't know how to add more than one. But anyway, if you see here, it reached to 130, and this one smaller than 130. So there is clearly a different, in terms of elasticity, the yield stress starts here somewhere 0.2, right? It's 0.25, yeah, somewhere here. It's exactly the same, quite the same. But this one has higher initial yield strength. It's somewhere in here. It's here, so it's lower, right? You can try it in your Excel. I don't have Excel in my computer, so I cannot really compare it, but I'm sure you can. Yeah, if I pull it like this, because that's 1000, right? This guy is 1000, this guy is 1000, so it's clearly higher. So how much is higher than tensile will be dependent on the friction angle. So that is the Drucker-Prager pressure dependent model that is usually used for polymers. So imagine, guys, now you have a question. Imagine, Dito, I have a tensile test of polymers. I do the tensile test, and I also have compression test. How do I find the friction angle? Trial and error. You put the tensile test data to your simulation, and you use, for example, a small value of beta, for example 5%, and then you run compression test. You get the compression data compared with your experimental compression data. Does it fit or not? If it's still lower, make the beta higher again. Make 10 now, and then compare again, and then, yeah, it's like iterative method, right? Until you finally match them. And yeah, that's it. And I hope this video is interesting for you guys, and you think it is useful for you. Please don't forget to subscribe, so it will motivate me to make another useful videos. And please like and share. Bye bye.